So good afternoon, everyone. My name is Gert-Jan Sulla. I'm a PhD student at the Faculty of Business Economics at Hasselt University. And one part of my job there is to teach data analysis and teach R at our first-year students of business engineering. And this year we gathered some information on how they learn and how they score on their assignments, and that's what this talk will be about. So to start off, I want to ask you a question, which is, how did you first learn to do your data analysis? And probably for most of you, the answer will not be R. It will either be something like Excel or SAS or MATLAB or SPSS. And then finally, when you were fed up with this tool, you went to R. But learning R at that point was not so difficult because you had a solid foundation to build on. But this has also to do with that R has been gaining popularity only recently. But can we also learn R if we are we have a limited prior knowledge? So let's say we just go to our first year of university after high school. Well, last week I asked this question on Twitter and LinkedIn. Some of you may have answered about how old you were, and I'm not saying that there is a right age or that there is a wrong age to learn R, but we see that most of us were in our 20s and the majority also above 30 years old, which means that we all had this solid foundation of programming experience and experience using other data analysis tools, which helped us learning R. And only a minority of people learned R when they were under 20, when their foundation, their prior knowledge was limited. So typically, R is not the first step into data analysis, but it can be. We all already have seen some very good examples at this conference. For example, the keynote yesterday by Mine was a very good example. Also, the other talks in this session. But also at Hasselt University, which is a small university about 70 kilometers to the east of Brussels. It's the smallest university of Flanders. We started this year by teaching data analysis to our business engineering students in their first year. So we are talking about 18-year-old students who come to study business engineering, and we give them the course which is called Exploratory and Descriptive Data Analysis. And what's important here is that they are business engineering students. So they are not statistics students, they are not computer science students, they are not actually expecting to be taught data analysis. There will be some future business data scientists, hopefully people going into business intelligence, but there will also be many more other different profiles like auditors, marketeer, logistic experts. But we believe that in each of these different profiles, data analysis is a must and is a required skill, but they do not necessarily expect it when they go to study business engineering, so there is a little bit of a motivation problem. But although they're different profiles in the end, their state at this point, where it is important for us, is very much the same. So no one had previous experience with R, and only a minority had some previous experience with programming. We were actually surprised that the 29% was quite high, but we didn't know what type of programming language that were taken into account by the students when answering this questionnaire. So probably there's maybe also some HTML or CSS in the 29%. But we need, in this case of limited prior knowledge, we need some extra, let's say, ingredients to guide these students. And the first ingredient is actually the environment in which the students start studying R. And actually, the environment at Hasselt University is quite perfect for this, because since we're a small university, we go by what's called guided self-study. So we do have the large auditorium lectures with the professors in the front, but we also do have a lot of small group sessions when there is a lot of interaction between professors, teaching assistants, and students, where there is a lot of individual feedback. We are very student-focused. There is a very low power distance between students and professors. We almost know all our students by their first name. Students are not afraid to come to our offices and ask for help if they have a problem. So we have this nice environment. And the second actually important ingredient is the content that we are giving to them. So the course is about exploratory and descriptive data analysis. It runs for 11 weeks. So we have the 6 lectures for the whole group together, and then we have 13 work sessions in smaller groups to do the practical things. And the content is actually very much in alignment with the tidyverse and the R for Data Science book. So we start with some basic R about knowing what is a vector, what is a data frame, and so on. And then we go to ggplot. And as we go along the way, we get to more complex situations. In the beginning, they will get a clean, tidy data frame. And as we go to the end, they will have to do also the tidying and the cleaning and the importing themselves. So this is a sort of accessible and consistent content that we are giving to them, which is also making it much more easier if they don't have this experience with other programming language of data or data analysis tools. But these 2 concepts are not enough, because you can create a perfect environment and give them the perfect content, but as they say, you can lead a horse to water, but you cannot make it drink. So these students are business engineering students, as I said, so they might not have an intrinsic motivation to learn data science, so we have to create some motivation. And one way to do that is by giving them practice assignments. So we made 6 assignments along these different topics, which allowed us to do some intermediate evaluation of our students and also to give them feedback along the way. So to give them some motivation to actually make the assignments, they were part of the final score of the course. They were set up as fill-in markdown files. So as an example, these are 2 questions taken from one assignment. So you can see that they are more or less closed-ended. So in the first case, they have to calculate correlations and they have to visualize it. So the second question is a little bit more open than the first one. But we do this closed-ended kind of questions because even if we have only 76 students, we don't have time to correct all the assignments for all the students. So we try to do some semi-automatic correcting and then do some manual correcting on the automatic tests that we did. So in the rest of this talk, I'm going to explain and show some results that we get from these assignments. So first of all, the question is, did they make the assignments? Well, we see that the majority of the students did. There was also only a small dropout. So at the last assignment, we still had 67 students out of 76 who were making the assignments. If we look at this from a student-based perspective, we see that 86%, so the wide majority of the students did all the assignments, and only a small group skipped 1, 2, or also some skipped all the assignments. So we have some small group of, let's say, the low achievers, the low performers, and we have the main group of students who are doing a lot of effort in this course. But making them alone will not help them to pass the exam. So we also look at their scores. Now in Belgium, it's typically that scores are given on a scale from 0 to 20, and everything below, above 10 means that the student passes. And if we look at the distribution of the scores for the 6 assignments, we see that the scores are quite good. This does not mean that our assignments were very easy. My students will testify that they were not easy, but this is actually logical because when you give them an R Markdown file and they see that their answer is not correct, they will try and try and try and ask for help at their colleagues, at their professors, at their teaching assistants to solve these problems until they are satisfied, and that's why typically they have this high score. But it does not mean that they were easy. In particularly, we see a small increase after the third assignment, where we had the complaint that they were putting so much time into these assignments that we had to make it a little bit more easier and shorter. Another thing that we can look at is the stability actually of the scores for a specific student. So we could look at individual patterns of these students, and we see a lot of variation here. So a lot of lines crossing, going up and down. So it does not mean that if a student does perform one assignment good, that the next will also be very good. So we tried to look more into this by actually, for each assignment, making 3 segments of students, so the low performance, so the bottom of 25% of students, then the middle and the top 25% students. And then we looked at how probable is it that a student transfers from one of the segments to the other over the course of the assignment. So we can look at the first probability when they start the course in which of the segments we will get. Of course, we will, in theory, expect here to have 25, 50, 25, but because there were some ties in the scores of the assignment, it's not well quite distributed. What's more important is to see what's happened after that first assignment, and then we look at this sort of first order Markov transition matrix, and we can look at the diagonal probabilities, and if these diagonal probabilities would be 100%, it would mean that students always stayed in the same segmented, so always making very good or always making very bad assignment. But that's not really the case. The only case in which this is almost the case is for students who skip the assignment. So skipping assignments was a very high indicator that the student would skip the other assignments as well. We see also that once you are in the skipped segment, the probability is also high that if you make the assignment, that it will be a low grade. And for the remainder, we see that there is a lot of regression to the mean. So good assignments means that the next assignment will probably be a little bit worse, and the other way around. But of course, we do not know whether these are random results or whether it is a reaction of the students who think, well, my last assignment was not so good, let's put in a little bit more effort in the next one. So there's also, of course, factors we don't know about. But understanding how students transferred from these segments and how they made the assignments, it's not the only thing. The second important thing is, what about the exam? If you look at the success rate of the exam, we see that it was much, much lower than the success rate of the assignments. Only 25% of students passed the exam. But this is, of course, logical because the content of the exam was totally different. It was on paper, so there was no opportunity to test their code. So it was more about insight into code. Do you see, you get a part of code, can you see if there is something wrong with it? Or can you explain this error, what do you do about it? So there was actually no opportunity to double check their answers, and that's why the assignment scores were a little bit lower. The exam scores, sorry. So if we look at the relation between assignment scores, so the overall average of assignments, and the exam scores, we actually see three groups. On the left, the lower left, we see the blue dots, which are actually our bad students who didn't make the assignments and didn't pass the exam. But then on the right, we see the students who have a fairly good score on the assignments, but not necessarily a good score on the exam. We see that there is a correlation where more on a higher score, closer to 20 on the assignments, will give a slightly higher probability to score high on the exam, but it's not really perfect. So we could ask ourselves the question, could we have known, could we have identified this group of students, even if their assignments were not immediately looking bad, that they were going to fail the exam? So could we have known? Well, first, rather naive thing we did was going back to the individual patterns and try to cluster them into different groups. And then you see different types of patterns. So the cluster one is where a student always performs very high scores, very steadily. We have the cluster 4, which is like the low performance category of students. Cluster 2, where there is a small increase in the third and fourth assignments and so on. And then we could relate this again to the exams, and we could see that for each of the clusters, the success rate was slightly different. The differences between the overall success rate are not that high, but what's more problematic is that we cannot use this clustering next year, because in week 1 after assignment 1 or after assignment 2, we do not have enough information to actually assign students to one or the other cluster, so we don't know which cluster their full pattern at the end will. So we cannot have like a quick alert that something is going wrong. So we tried something more sophisticated, so we went to predicting models. So just to be clear on the terminology, a true positive means that someone passed the exam and we predicted that he passed. So a positive is predicting a pass, and a negative is predicting a fail. And as input for the predictors, we used the scores, but we not just used the original scores, but we adjusted them for the complexity of the questions, which means a complex question has been given a little bit higher weight than easy questions in the adjusted score. And we looked also at variation of scores within each assignment by looking at standard deviation and interquartile range. And the idea is that not that we make one predictor about all the information on all the assignments, but we do it sequentially. So which means we do it, we use the classifier R from the R part package and support vector machines, and we actually predict after each additional assignment. We get more information about the students, and we look at the change in our accuracy, and we look at after more or less week 3 and 4, our predictors are above the baseline accuracy of 25%. What's more important than accuracy is actually, did we miss some students who were failing? Because that's just what we want to detect. So we looked at the false positive rate, which is the percentage of all the students who failed that we did not detect. And we see that it's dropping steadily. So already after week 3, if we look at the support vector machines predictor, we have it at 40%, and in the end we have it about 30%. And this is actually good because we want it effectively to be at 0. We even made another predictor, which is just the combination of these two, which is even more conservative, by saying that, well, if one of the predictors is saying to us the student is about to fail the exam, we're just giving the label fail. So it only has a small difference in the overall accuracy, but we see an even more lower false positive rate. But of course, there is a cost to this conservativeness, because on the other hand, we have a lot of students that will pass, but we have labeled them as they will fail, because a sure methodology to do not miss any failing students is to give every student the fail label. But there are also, of course, ethical aspects at work here, so it's more important that you try to help all the students who are about to fail than that you're helping students who don't have any problems. So that's maybe a waste of time, but it's not really a problem. So our conclusion is that these assignments can work both as a motivation for students, but also as an early alert system for teachers. So, and in the end, we also asked our students to finish, did they like it? Well, at the statement, this course increased my interest in data analysis. The results were slightly positive. I liked using R, not so positive. There was one who totally agreed, but there was also a large group that did not agree. So remember, these were business engineering students. They're not statisticians, they're not programmers, so not all of them liked using R, but they did recognize that R was a valuable skills to their tool, to their skill set, was a valuable addition, and also it fascinated them to do data analysis, but maybe not just in R. So to conclude, we had these 3 ingredients which show that learning R with limited prior knowledge is possible, but it just requires a different mindset and sort of different guidance for students, and that's where I want to stop. Thank you.
Thank you very much. There is time for questions. Yes?
Thanks. Why do you think, in your opinion, that they didn't end up liking R in spite of using tidyverse?
Sorry?
Why do you think, in your opinion, that the students end up didn't liking R in spite of using tidyverse?
It's part of what also was said yesterday. It's about the balance between challenging and be not intimidating, and I think at some point we crossed that balance a little bit more so that they had some negative experience with assignments taking too much time. So it's probably like more temporary effect that they didn't like R, that it was a little bit a negative experience. So I think that if you have this balance a little bit more between challenging and not intimidating, if you have that balance more right, then you will avoid this negative reaction.
Okay, more question?
So So have you considered giving them a practice final exam? Because I think it's a little cruel. So a lot of students, I've noticed, get really scared if they're given a problem where they have to know a function or know the arguments within the function. And I predict that your survey results were probably based off of that final exam being scary for them. Have you considered giving them a preparation exam or maybe making half of it take home? Or?
Well, in this results are about the relation between assignments and the exam, but not between the assignments and the final score, because that's actually like a weighted average between the scores on the assignments, which were practical, and the scores on the paper exam. So the paper exam is also because we also teach them more the theoretical concept of like outlier detection, for instance, or univariate and bivariate analysis. So we also have to evaluate that part, and then we try to be more ask them more insight questions about R. So I think it's a good combination to have those two.
Thank you for a nice talk. I have a question I didn't quite get. Do the students get the label on during the course? Do they understand that they are the failure
So the predictor
students?
is only made now, but we want to use it in the future to have like an earlier alert system when students are troubling. So even if we don't have a very large group, it's very difficult, even in the small group sessions, to know how each and every student is doing and to filter out which students are doing well and which need extra help. So we try to get with this model, this predictor model, to the next year and then see if these results would be helpful.
So you will tell them you're a failure student, our model predicts you're going to fail this course.
Well, we just want to help them. So if we see that someone is a failure student, it's not telling them, but it's just why is he failing and can we give him a more individual feedback.
It's a good motivation in any case, isn't it? Yes. Thank you.
Thank you very much. And I would like to thank all the speakers in the session once again, and for you that came for the session. Now we can go to the coffee break.